You're listening to Materials Business, the podcast where engineering, leadership, and innovation meet diversity and inclusion. Hosted by Monica Hernandez, engineer, entrepreneur, and industry advocate. When we embrace different perspectives, we create stronger industries, smarter solutions, and lasting impact. Now, let's dive in.
Good morning, good afternoon, or good evening, depending on when are you watching us, and thank you for being part of the material business community. My name is Monica Hernandez, and I'm your host, and I have a really, really impressive guest that we met a long time ago, and we have been planning this episode for a long time. Akhil, thank you so much for being here.
Thank you so much, Monica. I really have been excited for this podcast. Super excited.
Amazing. So we're going to tell our audience what we're going to talk about. We're going to talk about how we balance that engineering deep understanding of problems with financial impact. And we're going to talk about aging infrastructure. We love talking about that here and how we can intersect all that together. And your research has been super amazing ever since I saw you for the first time. It's been something that I am very curious and we are doing in industry. So it's extremely relevant for everyone in the podcast. So I'm very excited to have you here. So why don't you tell the audience who are you?
Yeah. So again, thank you so much for the warm welcome. My name is Akhil Reddy Chopra, and I'm currently doing my Master's of Materials Engineering at UBC in Vancouver. I specialize in pipeline corrosion. So we explore the world of pipeline integrity, but from a corrosion and electrochemistry point of view. And my work, as Monica alluded to, explores aging assets and how we can further extend the value or the life of these assets when exposed to new environments. And of course, what are the ranges of metallurgical integrity threats that exist can counterbalance some of those cost forward initiatives that we're looking for. For my side hobbies, I do a lot of hiking. It's in British Columbia, so it's the perfect place to do that. But I am also interested in bridging my own metallurgical expertise to one of my main passions, which is exploring history and ancient civilizations. And so on the side, I also do, similar to what Monica is doing here, I also run a podcast bridging ancient civilizations, history, and culture with technology and science. So exploring the different methods of metallurgy from ancient India, for example, learning about Damascus steel or how rhinoplasty and plastic surgery existed thousands of years. So those are some of my interests. And yeah, I'm just really excited to dive deeper into the work that I'm currently doing.
We need to have another podcast and you have to come and
Oh,
show
yeah.
us all those cool things. I had some in mind. There was this lady, she does a really good work on archaeometallurgy and she's in Argentina and she
Oh,
came
wow.
and
So
the
cool.
minute she was describing herself, I was like, oh my God, this is like Indiana Jones for
Yes,
metallurgy. And I was like, oh, this is so cool. So
so
first I need to
cool.
connect you with her first. And then second, you need to
Oh my
come
God.
and give us another podcast on that
Oh
topic.
yeah, 100%. Would love.
Awesome. All right, let's talk about aging infrastructure for today.
So I can share my screen.
Absolutely. So is for people that are listening to this, we are going to have slides. So if you're on Spotify or Apple Podcasts or any of the other platforms that is only audio, and you want to see the slides that are presented, you're welcome to go to our YouTube channel and then you can see the slides that Akhil is going to present to us. Perfect. I can see your presentation.
Okay, so really excited to get into some of the ongoing work that I'm working on at UBC. So the title of my presentation today is Repurposing Legacy or Vintage Natural Gas Pipelines for CO2 Transportation. And this work is done at the University of British Columbia, and my supervisor is Professor Edward Aswan. So to understand the urgency of the metallurgical assessment we're about to do today, we have to look at the scale of Canada's decarbonization plan. So we're currently aiming for a 48% reduction in CO2 emissions by 2030 in order to limit global warming to 1.5 degrees Celsius. So this translates to a massive 443 megaton emissions target, requiring a 35% cut from our current operational levels. As a lot of you may know, 55% of these national emissions are directly tied to the oil and gas and transportation sectors. So we are faced with an engineering hurdle. Essentially, we're not just here to capture that CO2, but we need methods of moving large volumes from these industrial clusters to geologically suitable sequestration hubs or utilization facilities. Now, looking at the current landscape, we're not starting from scratch. In fact, Alberta is a global leader in this, starting with the Alberta Carbon Trunk Line, which is the world's largest CCS project, which basically captures CO2 from the Northwest Redwater Partnership Refinery and the Nutrien fertilizer plant in Redwater and transports that CO2 to mature injection wells in Clive. This is a 240-kilometer pipeline transporting 14.6 megatons of CO2. This roughly translates to 2.6 million cars, being taken away from the road. And so there's a huge offsetting capability of this plan. But the total project capital was $1.2 billion. Another major project underway is the Pathways Alliance project. This is a joint venture between Suncor, Cenovus, Canadian Natural, Imperial, MEG, and ConocoPhillips. Essentially, the project proposes a 400-kilometer main line with a capacity for 2030 of 10 to 12 megatons per year, eventually scaling it up to 40 megatons per year by 2050. So this would link 13 and eventually up to 20 facilities to underground injection sites. And again, looking at the exorbitant capital cost of $16.5 billion. So as we can see, we are faced with an immense capital hurdle. And the question is, can we build our way to 2030 in time to meet our, our rising global emissions reduction plan? And the question is, how can we achieve immediate decarbonization milestones while drastically lowering those capital barriers? So this brings me to the core part of the research, which is there a case for repurposing existing assets, oil and gas or natural gas pipelines, whether they're vintage or, installed in the, early 2000s, let's say. So we do have examples of pipes that have been repurposed with significant cost reduction, starting with the West Glenville project in the US, which converted a 50-mile, 16-inch natural gas pipe. This pipe was originally installed between the 1960s and 1950s for $5.2 million. So we see a significant $35 million reduction compared to new build estimates. Secondly, there's the OCAP pipeline in the Netherlands, which repurposed a 51-mile oil pipeline. This was originally installed in the 1960s to deliver 3 megatons of CO2 annually. And finally, the number 10 feeder in the UK. This pipe specifically was installed in the 1970s, and it's part of a larger project of a 174-mile conversion. So again, significant cost reduction, roughly half of a dedicated new line. And as I was doing further digging, a study was conducted by DNV where they found that there's a significant capacity for repurposing pipe. over 58,000 kilometers of European pipelines have been confirmed for these repurposing projects. And that is equated to 53 to 82% of a cost reduction. But now that we've looked at the financial incentive, of course, for repurposing pipelines, we have to acknowledge from the engineering perspective that there's always going to be a trade-off. We might have our goal or intention of satisfying our financial needs, but we have to look at the reality. And I first want to talk about the thermodynamic constraints that we're limited by. So CO2 is specifically transported in its most efficient state if it's in the supercritical phase. Essentially, what that means is CO2 behaves like a dense gas. So it has a density similar to a liquid like water. I believe it's 50 to 80%. But it also has low viscosity, so it is still a gas. And so this occurs at 31 degrees and around 1000 psi. And so the safe operating measure for supercritical CO2 is between 1250 and 2200 psi. Now we can see that's significantly larger than what many of these vintage pipes are rated for, which is around 500 to 1500 psi. And so this can be quite significant in terms of some of the integrity threats to be seen. Significant frictional losses from two-phase flow, lower throughput, as well as integrity issues such as rupture or cracking if specifically the internal pressure of the pipe exceeds the ultimate tensile strength of the steel. Then we start to see a lot of material-related issues. From some of the examples I showed before, the CO2 is generally transported in the gaseous phase, which is meant to be the safest route in order to avoid two-phase flow, where we can operate these lines within the design limit of these pipes and also avoid some of those integrity issues that I mentioned. So repurposing seems to be more plausible for short distance and modest quantity transport. So I included this slide just to show again the percentage of vintage pipelines that exist in the US. So if there's 300,000 miles of transmission pipe, 62% of those were manufactured between the 1940s and 1970s. So that's a significant scale of vintage assets that are in operation today. While we looked at the thermodynamic constraints, we're also limited by the material constraints, specifically composition and manufacturing, where we see simplified chemical composition, so typically a higher carbon content, as well as low control over sulfur content. At that time, between the early 1950s, we wouldn't have seen as much control on desulfurization practices as we do see today. And so just commenting on some of the metallurgical concerns we have. One, of course, is as the pipe ages over time due to temperature and environmental fluctuations, we can see processes like solute diffusion, precipitation, or grain boundary decohesion. And this can express itself as, precipitation in terms of carbides or manganese sulfide inclusion present, which can act as either stress concentrators or trap sites for hydrogen accumulation. Also, as I mentioned, low control over impurities like sulfur and phosphorus. Again, from scrap variability at the time, contamination, and low trap element removal. And as I mentioned just now, high sulfur content can result in manganese sulfide inclusion. These are essentially more ductile compared to the base steel. So during pipe rolling, these sulfide inclusions can align itself with the rolling direction. And then this can cause anisotropy in mechanical properties like tensile strength, ductility, and fracture toughness. So these are just some images showing specifically the middle image, we can see, the banded or elongated stringer sulfide inclusions compared to new steel where they add calcium, which helps essentially, I'm not too familiar with the process, but it essentially breaks up those sulfide inclusions into globular smaller size, which are then more dispersed within the lattice, within the steel lattice. And today I also want to focus on a concern of hydrogen absorption, so leading to hydrogen embrittlement, cracking, or blistering issues. So when we're looking at repurposing vintage assets, we are also interested in the cumulative history. So what has accumulated over the lifetime of that pipe. And typically a lot of these lines were serviced for sour and sweet natural gas transport. What those two words refers to is the concentration level of hydrogen sulfide. And so if for whatever reason these lines had poor dehydration, we would see that hydrogen sulfide dissociates in a brine environment and forms sulfurous species as well as hydrogen protons. And so the mechanism for how hydrogen absorbs into steel occurs from two areas. One is internal corrosion. So now let's say we have an aqueous environment within our pipe. We have our anodic oxidation reaction of steel oxidation. And then to support that reaction for charge balance, we have the cathodic reaction of hydrogen evolution. So we can see that protons accept an electron to form hydrogen gas. And where do these protons come from? Well, as I mentioned, if we're having hydrogen sulfide dissociation, which also generates protons, then this becomes the source for the cathodic reaction, which then also drives corrosion within that pipe. And then, of course, also cathodic protection is an issue. So, of course, if the intention is to protect our pipe, if we apply negative potential or negative current, we're also if there's areas or pockets of moisture within that pipe, during cathodic protection, we're also essentially driving that cathodic reaction. We're driving hydrogen evolution. And so we might also see further generation of hydrogen atoms within the steel. And what does that look like? So essentially, if we look at the cathodic reaction, before hydrogen gas is formed, H2, we have single atomic hydrogen atoms. So just single H's essentially being adsorbed on the steel surface. And when two of them combine, they form hydrogen gas. But just before hydrogen gas is formed, those single H atoms can diffuse through the steel lattice. And specifically, they can accumulate at defects, which over time can build on its own partial pressure within that steel. And if that exceeds the steel's tensile strength, we may see blistering or hydrogen-induced cracking propagate within the steel. And so I did want to just briefly mention that there are two trap sites where hydrogen can accumulate, those being reversible and irreversible traps. So reversible traps refer to fast diffusion pathways like grain boundaries, dislocations, or lattice vacancies, and they have a much lower trap binding energy compared to irreversible traps where, if you think of a highway and you have cars and then there's a sudden crash on that highway, then you start to have a much slower flow of traffic. And that's exactly what irreversible traps are. They basically act as a sink for hydrogen accumulation within incoherent interfaces. And we typically see these around manganese sulfide inclusions as well as complex oxides. So again, as I alluded previously, manganese sulfide inclusions can be a deep trap site for hydrogen accumulation. Okay, so now that I've looked at the market value of these aging assets as well as the metallurgical concerns, this brings me to my research, where I worked on a case study of a decommissioned 1950s natural gas pipeline. And so I have three objectives. One was first doing a metallurgical characterization. So we looked at the microstructure, the mechanical properties of the vintage pipe compared to modern standards. And then we also looked at the effect of hydrogen absorption. So let's say this pipe was exposed to a sour gas. And then we would want to see how, based on the microstructure that we just previously assessed, how that hydrogen is accumulated in those inclusion sites. And then when exposed to a new CO2 rich environment, so during that transition from old to new environment of CO2, how does this hydrogen surface damage behave or accelerate, let's say, corrosion of steel? And then finally, I have some images on both pre and post corrosion blister attack. So this was a few images of the pipe that we received from a company that I cannot name. And we extracted tensile dog bone samples and coupons for the test from various locations along the circumference of the pipe, 0 degrees referring to the weld line and 180 referring to furthest from the pipe. And we also extracted samples along the weld line as well as transverse to the weld line to assess any potential anisotropy. So I want to mention that when we first received the steel, we were operating in the dark. We didn't know the service history. We didn't know the chemical composition. And so I had to perform something that's called spark optical emission spectroscopy, OES, where we can essentially obtain the chemical elements of both pipes. And I specifically want to comment on the high carbon content we see, 0.31% compared to 0.22% of carbon. Now, and also looking at the carbon equivalent. So what this means or what this tells us is that back then, manufacturers would rely on tuning the carbon content for increasing the strength or hardenability of that pipe instead of utilizing more recent alloying additions like niobium, titanium, or vanadium to also tune the mechanical properties. So back then, majority of the pipes, they had simplifying composition. And so according to pipeline welding standards, a carbon equivalent value exceeding 0.43 is widely recognized as a threshold where hardenability can increase, and this can also lead to hydrogen cracking. So the vintage steel, as we see, is greater than that value. And of course, with a higher carbon content, we can also expect heavy perlite banding, and this can also contribute to increased mechanical strength, as we'll later see. I also want to comment on the high sulfur content. So in the vintage steel, it's 0.04 compared to the 0.01. This also exceeds the typical maximum limit of 0.015 weight percent, which is seen in API 5L for X42 and X80 line pipe steels. So this can also imply a dirty steel prone to high density of manganese sulfide inclusion. Okay, so in this image, we can see the microstructure of both image A in the X65 steel and image B, our vintage steel. So note in image A, we see a relatively uniform distribution of polygonal ferrite. Also with some areas, so if you look at the pearlitic phases, we see bainite as well as some needle-like or side plating of ferrite perlite. So this is also known as Wisman-Staton ferrite. And this can also increase the strength of our steel, but of course that has to be well distributed, which we can kind of see from the morphology of image A. Versus in image B, for the vintage steel, we do see both coarse and fine grains of ferrite. So we can see In, let's say, the perlitic depleted regions, we have a greater accumulation of coarse-grained ferrite. And in the perlitic rich regions, basically the areas that show more black color and contrast, that the ferrites are finer in. Also, there are areas of banding, as I've labeled on the image. So essentially, we can see that this microstructure has a more heterogeneous appearance, and that will correspond to the mechanical properties in the next section. Okay, so from these images, I tested, or I was observing the yield strength, failure strength, and the percentage elongation of our steel dog bone samples for vintage and X65. On the x-axis, you'll notice the various locations along the circumference of the pipe, and then the data points. The red refers to transverse or perpendicular to the weld line, and the black data points refer to the along the weld line or parallel to the weld line. So what we can clearly see right off the bat is anisotropy, right? So generally, we would want to have similar properties between both the longitudinal and transverse dog bones, but we can see from the yield strength that those are deviating in opposite directions. Also, the values are also differentiated along the circumference of the pipe. I specifically want to comment on the failure stress and percentage elongation. Under loading along the longitudinal direction parallel to the weld, we can see deformation proceeds along the, like we can expect or hypothesize that deformation existed along the inclusion orientation. So if those, as I mentioned, again, those inclusions, if they were elongated and rolled in that same direction, then we would expect to see higher ductility versus transverse to the direction. If we apply a load perpendicular to the elongated inclusions, then we observed a lower fracture stress and also a lower percentage elongation, which corresponds to the ductility or the brittleness of the material. And so we can see orientation dependent properties based on hypothesized orientation of our sulfide inclusions. So this is very interesting information. And I confirmed the presence of our sulfide inclusions from doing EDS analysis on the fractured surface. So image figure 9, we see stringer inclusion. So it kind of looks like a flattened pancake, let's say. An area 1 and area 2 is a region of no sulfide inclusion. And from the spectrum, we can see area 1 does in fact have sulfur and a high degree of manganese compared to spectrum 2, which is mainly just the iron manganese lattice. And I also conducted EDS and EPMA on a variety of different inclusions that I detected. I want to specifically highlight the colored EDS image. Essentially, it shows a mango-shaped manganese sulfide inclusion characteristic of silicon-filled steels. The architecture is a result of a two-step formation process. So the silicate caps formed first during the oxidation. They act as seeds for the manganese sulfide to nucleate onto as the steel solidifies. So during hot rolling, the soft sulfide core was likely squeezed into the stringer shape, while the hard oxide caps resist deformation. So mechanically, these are critical failure points where we can see thermal expansion mismatch between the brittle oxide and the steel matrix, which creates stress concentrations that can trigger micro voids. Furthermore, the sulfide core is chemically active, making these inclusions primary targets for pitting and hydrogen trapping. In figure 12, again, we can see that stringer-like. So that one manganese sulfide, that black inclusion, is quite elongated versus the lighter region, that globular inclusion, was actually a mixed oxide containing, I believe, aluminum, silicon, and oxygen. So again, just pointing to the morphology of various inclusions and oxides. And then the final step to our materials characterization is running hydrogen permeation tests. So we want to see, based on the microstructure, how susceptible is the steel to hydrogen penetration. So this tells us, again, the intensity of hydrogen trapping based on microstructure and inclusion. And so this is just one of the corrosion or electrochemical techniques where we have our steel membrane in the center. The left side, we're essentially generating hydrogen by applying a negative potential to drive the hydrogen evolution reaction. Once that hydrogen adsorbs onto the steel, it diffuses through the membrane, where when hydrogen exits the membrane, it's immediately oxidized, and we impose a positive potential. And so this image just explains that setup. And from these results, we obtain these permeation transients, and we see two very different integrity stories. So this oxidation image essentially corresponds to, as soon as that hydrogen exits the steel, it's oxidized. And so that oxidation current refers to exited hydrogen, right? So from the vintage steel, we can surprisingly see a shorter incubation time. So that's the black line. When I mean incubation time, that's where we essentially have no current and then a sudden spike in current. So that's when the first hydrogen exits the steel. And so that has a surprisingly lower incubation time compared to the 65 steel. And this suggests that the vintage steel has short circuits or fast diffusion pathways initially, allowing hydrogen to suddenly pass through that steel. And that is, again, likely due to the morphology of having those elongated stringer inclusions, or also heavily banded. If you have that banded ferrite perlite in between, essentially those interfaces, hydrogen can pass through. But then, as we see over time, over the next 70 hours for vintage steel, we see a continuous decay instead of a steady state plateau, which is observed in X65. And this essentially tells us that these inclusions are, over time, continuously trapping hydrogen. And so it's slowing down the mobility of hydrogen through that steel, and we're not seeing a equilibrium develop over time. Okay, so very quick summary is we've looked at the presence of inclusions and how it corresponds to anisotropic mechanical properties, as well as the hydrogen transients, where initially morphology of inclusions as well as microstructure can contribute to fast diffusion pathway, but then over time can act as deep sinks for hydrogen accumulation. And so now I'll go very quickly because I know we might be losing some time, but now that we've looked at the metallurgical history of the pipe, we've understood the pipe. Now, of course, the next step is to see how it behaves in a new environment, in the CO2 environment. So what I did was, as I mentioned, if we recall from a previous slide, we need to look at the memory or the history, the accumulated history of that pipe. And if a lot of these pipes were exposed to sour gas conditions, I wanted to simulate the worst case of hydrogen damage on my vintage steel. And then once I've simulated that hydrogen damage, I take these samples and I expose it to a new CO2-rich environment where I look at the corrosion behavior. So my main goal was to see, how does hydrogen damage affect the corrosion properties in a new CO2-rich environment. And so initially, in order to simulate worst case hydrogen degradation, I didn't really expose that steel into hydrogen sulfide. In research, we can accelerate our conditions. And so what I did was I applied a negative current and I forced hydrogen evolution reactions to take place by generating hydrogen on the surface of steel. And I did this for various samples and I changed the charging time. So I charged steel between 2 hours and 60 hours. And this, of course, changes the concentration of hydrogen within the steel. And as we can see here are some interesting images. So in figure 16, A and B, A refers to an image that has been charged for 2 hours versus 60 hours. We can see an incredible increase in both the size and the population density of these blisters. In figure 17, we can also see, again, the first image corresponds to the 2-hour charging condition. So we see essentially a lift in the steel matrix. And then as we progressively increase charging, not only do we have, these larger blisters, but also smaller blisters concentrating around the initially formed blister. And of course, under severe charging, that's when we start to see severe cracking. So for the electrochemical performance of the steel, so as you can see in figure 18A, I conducted potentiodynamic polarization tests on all of my steel samples, with the control being this black line. So that the black data shows uncharged steel, so at the 0-hour condition. And then all of the colored lines below refer to the hydrogen charged steel between 2 and 60 hours. And what we can clearly see is that the corrosion rate does in fact increase and significantly increases, especially after charging to 36 hours and beyond. And so we can see also from our polarization data that the OCP, so when we are not applying any potential, that the OCP value also decreases by around 50 millivolts. And so this essentially shows that corrosion does in fact increase. Now, there may be two reasons for this. One, of course, is the increased surface area, right? So at 60 hours, the actual surface area of the steel is no longer the same as an uncharged clean surface. Now that we have blisters, we're increasing the surface area, and therefore the current that we generate would also increase in magnitude, right? But I also, what I don't show here, I also performed EIS tests. So these are electrochemical impedance tests, where I wanted to look at the charge transfer resistance of the steel. So basically, it's the willingness of that steel to give up an electron. And what I found was right when I removed the steel samples from the charging electrolyte and immediately placed it in the CO2-rich solution, I saw that the charge transfer resistance decreased as I increased this charging time. So that also tells me that before I apply any positive potential to oxidize the steel, right around the open circuit potential, the natural potential of that steel immersed in solution, we see that the steel is willing to give up an electron or oxidize itself. And so that also tells me that it's not just a surface phenomenon, but the hydrogen itself, if hydrogen atoms are within the steel, the iron lattice, those areas become high strained regions where, compared to the base lattice, because of that highly strained area, steel may be more willing to give up an electron and oxidize. I also performed, as you can see here, CM images on post-corroded samples. So these are the blistered samples immersed in the CO2-rich media. And what is very interesting is we see localized attack, right? So in all three images, which is essentially the same location, these were all exposed to our electrolyte. right? But we can see the base steel, right? So the clean steel without any blisters doesn't really show localized attack, which is expressed through, um, the contrast in color, right? Compared to these blistered regions, if we look at figure B, which corresponds to the backscatter SEM images, it shows a defined etched microstructure. So we've been able to etch the surface with our corrosive electrolyte and reveal the underlying microstructure. And so it also points to or tells me that if these regions are under high strain and we're more willing to oxidize, we can see that expressed through these images compared to the base steel. So, and then in figure C, those two those two areas were blisters. So those were distinct blisters that were formed, and we can see around the periphery, around the perimeter, as well as on the blister cap, both have been localized, both have been attacked locally. And so this is quite interesting for me to see how hydrogen can in fact accelerate corrosion in steel. And so essentially for our conclusion, we've assessed the metallurgy of the vintage assets. We also looked at the corrosion kinetics and how blistering can potentially accelerate corrosion in steel. Um, Basically, we have to see that there's always going to be a trade-off between the engineering and then our financial incentives that drive industry. And so I have a few key points on requirements for successful CO2 deployment, right? And so if we are to use vintage assets, we have to ensure stringent dehydration. Uh, well, this applies essentially to all pipes, right? As soon as you have hydration, you have corrosion risk. But specifically, we need to look at inclusion mapping, right? Because depending on the environment, so whether it's CO2 or other types of environments, that the steel essentially acts as our blueprint, right? And it can tell us, we can kind of forecast what kind of issues can occur. So we need more monitoring, and we also need hydrogen barrier coatings. So what I found was a lot of carbon steels in the CO2 industry are in fact not having any internal coatings. They're bare steel. And so this, of course, is the biggest issue because if we want to prevent any hydrogen attack, we need a layer of coating to prevent that hydrogen diffusion through steel. So this concludes the research that I've done thus far. These are my references, and I hope it was informative enough to learn something new.
It was amazing. I always joke that what would have been of a materials engineer presentation if they don't put microstructure pictures?
You can.
You can, right?
It's integral.
Yeah, it is like, okay, yeah. How can I explain that? A microstructure. So really cool. I loved it. You transported me into, 25 or more years, I think, more than that. Oh my, of when I was like you in the university and getting all those studies. I have one question is, can we do all of this is done obviously from samples from an actual pipe that you got the opportunity to cut. Sometimes I die for those opportunities and they're rare in the industry. They're like, no, let's just plug the tube and then we need the equipment. They're like, oh my God, okay. So can something like this be done without the actual sample, or what kind of information will we need from the asset that is being operated? Maybe not to get to the point that you are, because obviously nothing replaces a piece of microstructure or a piece that you're able to actually put under the microscope, but something similar. Is it something that could potentially be done without destroying or doing destructive testing?
Yeah, definitely. That's a great question because, of course, we can't take an entire pipe, dig it out of the trench, and put it in our lab. Like, does not happen. So what industry does is something that's called inline inspection, as well as non-destructive testing. So essentially, one of the main, I guess, ways of doing that is utilizing something called pigs. These are essentially smart technology tools that run inside the pipe. So when they want to essentially, they have to dehydrate or degas the pipe first, and then they pass these pigs, which are basically smart technology, and they use things like ultrasonic testing, essentially where they can detect cracks, deep cracks, subsurface cracks, or also surface cracks. And then that and that data is continuously logged for real-time data. And so that, that can give, without, of course, destroying the steel. So that gives inspectors an idea of, okay, these regions in this section of pipe, is exposed to, it may have been exposed to a corrosive environment, or there may have been pressure fluctuations in this specific region. So not only are we getting real-time data, but we're also getting where that data is coming from. And that's most important, is location-specific data. So that's done through inline inspection tools like PIGS. We can also do coding detection tests or coding evaluation. So we can use coding gauges and essentially it sends a signal through the coding and can tell us the thickness of that coding. So of course, initially during manufacturing, you want to ensure that the coating thickness is uniform throughout. But of course, in industry, in the environment, you're prone to maybe erosion or soil displacement, or you might have landslides. So you might be continuously changing that thickness of coating. And so that also needs to be monitored and measured over time. And we have the tools to do that.
Amazing. Holistically looking at the whole process on the whole life cycle. We do that every day here, but it's just amazing to see how we can get to the same conclusion, and we're just from different points of view. So it's amazing.
Absolutely.
Akhil, thank you. It was really good. We are really out of time, but thank you so much for coming. It was a really great presentation. I learned a lot. I'm sure the audience is going to learn a lot. The final question is, what is your message for those of the listeners that we have in this episode?
Yeah, that's a really good question. Something that I've also reflected on while I'm in research. And I think what I've learned from research is that we have all of the tools to perform our engineering, tests, experimental tests. And the expectation, what we want, may not always match with reality. And I sort of pointed to this at the beginning of the presentation, right? Is we might have our financial estimates. Industry always wants to reduce costs in the quickest, most efficient way, versus in labs, that's not possible because we're trying to look at worst case scenarios. We're trying to expand our ranges or our limits. Um, so expectation may not always align with reality. And especially if you're a young engineer or if you're a young scientist, that can be something to grapple with, right? Because we're results hungry. As engineers, we want to show results and we want to present them and hopefully have some positive impact to the work we're doing. But the reality is, we do also have to operate within fixed constraints. And I think that's where also the experience and maturity, I guess, would come from. I'm still trying to, grapple with that as I enter the workforce, as I graduate, and realize that in research, we have loads of time, but in industry, time is also a constraint. So that would be my message.
It's a really important message, and I don't think I have heard it in any other of the episodes. So thank you for bringing that up. Definitely, the velocity at what we operate is different in industry than academia. And then the more we are aligned and the more that we see on our purposes, that is, we can really excel. And then, hey, this is going to make a difference and this is worth investing in. And this is where real solutions come to play. So thank you for doing that work.
Thank you so much. I really appreciate the opportunity to present some of the work. So much fun.
That's sad. Yeah, it was really cool. Amazing. Well, we'll have you for another podcast. and to talk about the other subject. And to our audience, thank you so much for sticking with us. And we'll hear from another super amazing guest in the next episode. Thank you so much.
Thanks for listening to the Materials Business Podcast. Feel free to visit infinitygrowth.ca to see show notes and explore other episodes. If there's someone you think should hear this episode, please share with them. Take care of yourself and have a great rest of your day.